So we've come to the end of the conference, and it's my pleasure to introduce Uma Iyer, one of our own at CUNY. And she'll talk about the presentations of an algebra of quantum differential operations.
Thank you. I thank the organizers for giving me this opportunity. Thank you. And I also thank the Kulchin seminar for adopting me, even though I do not speak your language. So my talk is on representations of an algebra of quantum differential operators. Let me start with generalized while algebra. While algebras were introduced by Rosenberg and Bobula independently in the 90s. Here is the definition: generalized while algebra of rank 1. Start with a ring R and then automorphism of R. Let T be a central element of R. Then the generalized while algebra generated over this ring with respect to this automorphism and the central element is. It's an extension of R generated by two new elements, modulo these relations. Yx is the central element, xy is the image of the central element. X almost commutes with elements of the underlying ring. So does y. Notice it's the automorphism skew commuting and it's inverse for y. This new algebra A is free as an R module with basis x raised to n, y raised to n. The moment you multiply x and y, you land in R. Examples. Start with polynomial ring, one variable, t. That t is your central element. Define the automorphism to be the shifting map. With this automorphism, the generalized while algebra over kt is generated by two variables x and y. Yx is t, xy is t plus 1, that's the automorphism. And x and y skew commute with the underlying polynomials. In other words, notice xy minus yx is 1. So we have our first while algebra. Small change in your automorphism, notice. So same polynomial algebra, your chosen central element t, and the automorphism is qt plus 1. Construct your generalized while algebra. Here you get this relation, xy minus qyx is 1. That's the first quantum while algebra. Here is one more example. Start with polynomial algebra in two variables. Take little t to be one of those, and the automorphism is defined likewise. Yeah. Here, so we again construct generalized while algebra. You have two new variables, x and y, satisfying these two relations and commuting with the polynomials appropriately. And you get...
What is sigma t equals y plus h? What's that y then?
Is it supposed to be
Oh, I'm sorry, it is t. The wrong finger got fired. Yeah. So, right. So this is the enveloping algebra over SL2. Yeah. So the last example here. So you have t, z, z inverse, and your sigma is, on z it's just q squared z, so it's multiplication. So you know where I'm going with this, right? So this is the quantum group over SL2. Yeah. So weight modules. So they, you see, I'm looking for weight representations over an algebra of quantum differential operators. So let me first introduce weight modules. Start with a commutative ring R and let V be an R module. Max R is the max spec. For any maximal ideal of R, V sub M is the are all those vectors unhighlighted by M. So that's called the weight space corresponding to M, weight M. Support of V, all those maximal ideals where the weight space is non-zero. We say that V is a weight module if it splits into a direct sum of weight spaces. Now, so say you have a ring where you have a commutative subalgebra. So if V were an A module, then V is also a module over R. So we say that V is a weight module over A if V is a weight module over R. So in particular, let's start with a GWA of rank 1. So you have commutative ring and an automorphism of the ring. Take a chosen element T and let A be the generalized Weil algebra over R. We want to study weight modules of this GWA. So sigma, the automorphism on the ring acts on max spec. So let capital omega denote the orbit set under this action. Note, by the definition of generalized Weil algebra, X moves weight space up and Y moves weight space down. So this is also motivated by down-up algebras, if you have seen. So it's the same notion. So because of this, any weight module decomposes into submodules, you see, where V sub omega corresponds to the orbit little omega. Yeah? So every V sub omega is a submodule of V. So it's enough to study V sub omegas, basically. For any maximal ideal M, call M a break if T is an element of M, or chosen T. If it's an element of M, what it does is, you see, wherever the vectors which are unhighlighted by M get unhighlighted by T. That's why we call it a break. Let B be the set of all breaks. For any orbit, B omega, little omega, denote by B sub omega to be the breaks, set of breaks which show up in that orbit. So indecomposable weight modules over generalized Weil algebra rank 1 were classified by Drozd, Guzner, and Ovsienko. So they fall in 5 families, basically. Here, first family, your orbit is infinite. That's called linear orbit. And there are no breaks. An example of this is a telling example. So take a complex number which is not integer and consider over complex numbers, yeah? X raised to a times, what this means is it's a formal power of x's, and this is how Weil algebra, Weil algebra would act, because I'm allowed negative powers of x's. I have a chain. The orbit is infinite, both directions. Multiplication by x is a going up operator. Y stands for my derivative, Y is a going down operator, and because A is not an integer, my derivative is never 0. So I have an irreducible module there in this case. Second family, here again I have a chain, but there are breaks. An example of this is as follows. So take characteristic of the underlying field to be P, non-zero. Then view Kx, the polynomial ring, as an A1 module, the natural A1 module. So notice because characteristic is 0, you hit 0 several times. So what you have is not irreducible, but what you have is indecomposable. So here is an example of the same picture in general. I mean, I could have my A could be anything then. So I could hit 0 anywhere else. The next three families, family 3, 4, 5, we have finite orbits. Okay, they are actually more difficult to draw. So if you have a finite orbit and no breaks, this orbit is called circular. It's a finite orbit. For example, when characteristic is non-zero, then first Weil algebra has finite dimensional irreducible modules. Okay. Families 4 and 5 come from occur when your orbit is finite and you have breaks. So here you could I will not be able to do justice to the description here, but there are quite a few families. So okay, I will not say more. So is this okay? So there are basically 3 families when you have finite orbits. So okay, so what is the algebra of quantum differential operators I look at? I follow definitions and constructions given by Luntz and Rosenberg. They wrote series of papers in the 90s. Start with a field K and let gamma be an abelian group. Let R be a gamma graded K algebra. Fix a bicharacter. Now R is gamma graded. Therefore, for every element from your abelian group gamma, you have an automorphism actually, sigma sub A, which on R just spits out a scalar multiple of R. That scalar is given by your chosen beta. This is the grading operator. Sorry? All right. So let Z sub Q denote the quantum center of my bimodule, R bimodule, graded homomorphisms. So mind you, graded homomorphisms here do not maintain degrees, they could shift degrees. So what is the quantum center? Start with homogeneous homomorphisms phi, such that right R is just skew left action by R. So this is not even closed under addition, you see this set. So consider the K span. This is the quantum center. So if I use A bracket to be phi R minus sigma AR phi, so it's just the difference of the two actions. Using this, my quantum center is just the K span of all those homogeneous morphisms whose A bracket is 0. Okay. Zeroth quantum differential operators is the R bimodule generated by this Q center. Now, as in Grothendieck's definition, this is a nested definition. So, ith bimodule is R bimodule generated by those homogeneous phi's for which there is a degree such that that particular commutator falls in a lower level. Okay? So by a construction, you want bimodules at every layer. Okay? So you have a filtered algebra here. Okay? So in general, zeroth order quantum differential operators are given by left multiplications, right multiplications, and the graded morphisms. There are these relations automatic for every ring, gamma graded ring. Right and left multiplications commute. The graded operator almost commutes, both for left as well as right. So the main example I have looked with, this is joint work with McCune. Start with a transcendental element Q over Q, rationals, and my field contains QQ. Let R be the polynomial algebra. Polynomial algebra is Z graded, degree of X is 1. Beta be the chosen bicharacter given by this. So sigma be the automorphism, that's just multiplication by Q to the N. You get three different derivations. Del 1, that is a quantum derivation with Q. Del, the usual derivation. Del minus 1, there's a quantum derivation with Q inverse. So we could identify dQr in this case. This is generated by multiplication and these three derivations. In a joint work with Jordan, we have shown that this particular algebra is left and right Noetherian. It is a simple domain, GK dimension 3. Defining relations among these generators. Notice this is the Leibniz, and there is a quantum commuting among the two quantum derivations. This is something that it's not difficult to check, but happens. So it turns out these are the defining relations. So this is the algebra whose weight modules I wanted to study. Okay. Now, so the quantum derivations del 1x minus x del 1, it's the automorphism sigma. Likewise, del minus 1x minus x del minus 1, it's the inverse of sigma. Moreover, one can check del minus 1 is composition of del 1 and sigma inverse. In other words, among the set of generators, I no longer need del minus 1. So let tau be del x. Yeah? Then we notice that this algebra dq is generated over localization of a polynomial set, a polynomial ring, with generating set x, del, and del 1. In other words, dq contains two generalized Weil algebras of rank 1 over a commutative ring. So if I take x and del, I get the first Weil algebra over that particular commutative ring. If I take x and del 1, then I have a quantum Weil algebra. So now I can study weight modules of dq. So this is joint work with Fotoni. So start with an algebraically closed field. So we can extend irreducible A1 module to irreducible DQ module. An example of this, start with a field that is of characteristic 0. Then the action of A1 on Kx is irreducible. If Q were a root of 1, then the natural action of AQ on Kx is not irreducible. It is indecomposable. Okay. But together, together Kx is a DQ irreducible. Family 2, irreducible modules of DQ, which are extended from irreducible AQ modules. An example, start with something that is non-zero characteristic, then the natural action of A1 is not irreducible, although it is indecomposable. If Q were not a root of unity, then AQ acts on it irreducibly. So together, this is an irreducible DQ module. Family 3. Yeah. So here we have modules which are not irreducible either as A1 or AQ module, but they are patched in such a fashion that they form an irreducible DQ module. An example is this picture. So X is the going up operator. I have two operators. One is del, that gives me while algebra, del 1 that gives me the quantum while algebra. As long as I choose my A and B such that they are not simultaneously 0, I have an irreducible DQ module. But if they were 0 at different places, then this particular module is neither A1 nor AQ irreducible. So what we proved was when your field is algebraically closed, every irreducible DQ module, weight module, is indecomposable as A1 and as an AQ module. So in the same setting, algebraic closed field, the irreducible DQ weight modules that we saw in these three families, they are all. There's nothing more. So, almost done. We are at present investigating irreducible weight modules of higher rank DQ. In this case, both for the while algebra and the quantum while algebra weight modules have been studied, but not so much the quantum case. So, several works have been done though on the nth while algebra and the quantum. Some of the authors being Beckert, Benkart, Futoni, Hartwig. Thank you.
Do we have any questions? No, so if not, let's thank Uma Iyer.